The next speaker on the schedule is Eirik, who is also a postdoc at the Institute for Theoretical Astrophysics in Oslo, and he will discuss the calibration problem within BeyondPlanck. Thank you, Eirik.
My name is Eirik, and I am going to talk a bit about the BeyondPlanck approach to calibration. So first of all, a definition of the problem. What do we mean by calibration? The goal of CMB analysis essentially is to classify the radiation field of the CMB. So we want to know what the intensity coming from each point on the sky is. And so we point our detectors towards that point, and the detectors, they don't give us the intensity directly. And what they give us instead is a signal measured in volts. So calibration refers to the process of trying to figure out what the mapping between the readout and the actual intensity on the sky is. And the conversion factor between those is called the gain, G. And G is, it would be nice if G was constant throughout the whole experiment, of course. But unfortunately, it fluctuates, especially with the thermal environment of the instrument. And it's generally not constant in time nor constant between detectors. Estimating the gain is obviously quite important in order to classify these temperature fluctuations. And for Planck, it's also important for another reason, which is that because of this Planck scanning strategy, we need to use several detectors at once, or data from several detectors, in order to reconstruct the polarization field of the CMB. And if one of the detectors is wrongly calibrated, then that will leak into the polarization as well. So estimating the gain is of quite important. The data model that we use is what you just saw with from Håvard's talk. We have here the measurement in volts on the left-hand side, which we model as being the sky signal measured in Kelvin multiplied by the gain, plus the noise terms that Håvard talked about. As you can see here, we have a subscript here, T, which refers to just the fact that these are time samples given by the sampling frequency of the instrument, essentially. Whereas we use a different subscript for the gain. And that's because we don't assume, or we assume that the gain doesn't vary on such short timescales as the sampling frequency of the instrument. Rather, it has a longer variation. And what we assume is that the gain is constant within one scan. The Planck instrument scans the sky in great circles for about an hour, and then it readjusts and scans another great circle and so on. So within one such scan, we assume that the gain is constant. Another thing to note from this equation is that there are some degeneracies here that will show up. First of all, if we only have a measurement and we don't know anything about the gain or the sky signal, then we can adjust the gain up by a factor of 2 and divide the signal by a factor of 2 and essentially end up with the same measurement. So we need to introduce some kind of extra knowledge in order to be more efficient. The same thing goes for the correlated noise, as we shall see. The gain and correlated noise affect each other quite much. And so these degeneracies are not, it's not a showstopper per se when we are using the framework of BeyondPlanck, because what we want to do is to explore the posterior. But exploring the posterior goes a lot faster if we're able to intelligently break these degeneracies. So let's look at the gain and the noise correlations first. But this is a typical correlated noise map that we get from our current solution. We see that there are some structures here, but it's generally okay and well behaved. If we on purpose try to make a run where the gain, for example, is not allowed to vary in time, so it's a wrong model essentially, then we end up with the correlated noise map that looks a lot uglier like this. So there are clear correlations between how we model the gain and how we model the correlated noise, which we'll look at how to deal with, because the goal of BeyondPlanck is to map out this posterior distribution. We have all the parameters here: the gain, total signal, correlated noise, and we want to sample from the whole joint thing here, given the data. And when it comes to the gain, in the Gibb sampling framework, we want to sample from this conditional, given everything else. So this is the nice thing again about the Gibb sampling framework, is that we can assume that all of these are now essentially correct, and then just solve for sample the gain given those things. But let's now look a bit closer at the correlations between the gain and correlated noise. So we drop all these other parameters here and just look at the G given correlated noise. So as I said, they are quite correlated, and that means that their joint distribution, if we were to visualize it in two-dimensional space, for example, would look like something like this. And when we perform our Gibb sampling process in a very correlated space like this, it goes, it's very slow, and for the reason that we see here. Gibb sampling means that we fix correlated noise to a certain value, which is represented by this blue line here now, and then we sample from this one-dimensional distribution of G given everything else. But as you can see, if it's very correlated like this, then this distribution is very localized around this area where we already have the previous sample. So when we draw a new value here, it will be very close to the previous one. And the same goes when we slice downwards here and sample from the correlated noise given the gain. So when we repeat this process many times, we will end up with a lot of samples that lie very closely together, and we will not be very efficient in trying to map out this distribution. If we were able to somehow sample from the joint distribution directly, that would be a lot more efficient. So what we do in BeyondPlanck is to essentially treat the gain and the correlated noise as one parameter. Like we put them together in one set, and we sample from the joint distribution of those two parameters together as part of the Gibbs chain. And the way we do that is by using an identity from probability theory that says that a joint distribution is given by the marginal distribution over one of the parameters multiplied by the conditional of the other parameter given the first one. So illustrating this again, we still have this correlated structure between gain and correlated noise, but now this axis here shows or is given by the marginal distribution. So when we draw our sample, the marginal distribution looks like this because we're summing everything down to this axis here. And that means we're making a lot bigger jumps whenever we sample the gain. The correlated noise still is very localized, but that doesn't matter because we jump very far on this axis essentially every time we sample. So this is how we deal with this correlation between the gain and correlated noise in BeyondPlanck. Then the second problem was that of the signal gain kind of degeneracy. One way to, as I mentioned, one way to deal with this is to have more information. And what we could have more information about in this case is the signal. If we point our detectors towards something that we know essentially what the intensity of that object is, then we can compare the measured values with what we expect from in temperature space, and then the gain would be given by the ratio of those. So that motivates looking for such sources. And something that's been used in the CMB analysis or experimentation field are the dipoles. So, so I'm using this scientific picture here by some guy on YouTube, which shows that the solar system moves through space essentially, and of course it moves through space. But what's relevant here is that it moves relative to the CMB rest frame. So the solar system as a whole has a motion relative to the CMB rest frame. In addition, the Earth moves around the sun, and the Planck satellites moves along with the Earth. So the Planck satellite both moves with the solar system and it moves around the sun. So it has two peculiar movements relative to the CMB rest frame. And we know from relativity, when you move relative to something that emits radiation, if you move towards that object, it will be the radiation will be blue shifted. Essentially, in our case, it means higher temperatures. When you move away from it, it will be lower or red shifted at lower temperatures. And so in our case, because we have this movement towards and from essentially the last scattering surface, we would get this dipole when we subtract the CMB monopole. This is why we have this pattern. And we know the characteristics of this pretty well. When we, the way that this signal looks when we scan it with a detector looks like something like this. So here, the black line shows the solar dipole, which is what we call this dipole that arises because of the solar system movement relative to the CMB rest frame. And then the orbital dipole is this blue line, which is due to the movement of Earth around the sun. The solar dipole is very strong, and it's the strongest signal that we have compared to all the others here. The galactic foregrounds, for example, you see these red lines here. They can be strong, but they're not. The solar dipole will typically dominate. So in that sense, it's a very good calibrator. The problem with the solar dipole is that we only know the phase of it. We only know what the period here is. We don't know the amplitude. So the solar dipole is essentially one of the parameters that are part of our Gibbs chain, and so we have to estimate the solar dipole jointly with the gain. So this doesn't lift the degeneracy completely. The orbital dipole, on the other hand, we know perfectly well because we know how fast the Earth moves around the sun, and we know how strong the CMB monopole is. And so when we know those things, we can calculate this directly. So this is not part of the Gibbs chain. But the problem with the orbital dipole is, as you can see from this figure, that it's quite weak compared to the other signals. So that means that for short-term calibration, it's not very suitable. If the gain was constant throughout the whole mission, we could use the orbital dipole. It would be a great calibrator because essentially all the other signals would average out because the orbital dipole follows Earth's movement. It's not stationary on the sky. So we could use this to calibrate the whole instrument, but that's not the case, unfortunately. So what we want to do is to try to use as much of this as possible using the statistical certainty of the orbital dipole and the strength of the solar dipole, essentially. So this motivates splitting the gain into several components. So if we see the gain as a given one gain factor for each PID or scan given by this Q, and for each detector given by I, our model is that this gain can be written as an absolute term that is constant for all detectors and through all times, plus a fluctuation term that can vary between detectors, but that is still constant in time. And then finally, this fluctuation term that can vary in time and between detectors. And the good thing about doing this is that we can use, essentially now we split the gain into 3 Gibbs parameters, and we can estimate this one using the orbital dipole, and then estimate the 2 others using the full signal. So these 2 will be affected by the statistical uncertainty, but we have tied down a lot of the gain with statistical certainty using the orbital dipole here. If you want more details on how we sample each of these, they can be found in the paper on calibration that has been on archive for a couple of days now. We also impose these conditions that the fluctuation terms have to sum up to 0 in order to make these proper fluctuations from a mean. This time variable gain, when we sample it just like this, it ends up looking quite noisy. And this is not completely accurate, or we could do better, essentially. We know that the gain is correlated between PIDs, and so we follow the same approach as previous pipelines have done by essentially using a boxcar average smoothing window and smooth the PID so that it becomes the average of the neighboring PIDs. The smoothing window is given by the strength. It's variable, the size of the smoothing window, and it's given by the strength of the dipole. Because when we have a strong dipole signal, we have a high signal to noise ratio, and so we don't need as many points to get an accurate estimate. Whereas when the dipole is weak, we need more samples in order to estimate correctly. In addition, we have these sharp gain jumps that was mentioned in the previous talk as well, that are correlated with various events in the instrument, typically thermal switchover and stuff like this, or thermal events. And the point I'm making here is just that when we are smoothing, we don't want to smooth across these because these are obviously not correlated very well. So whenever we do the smoothing, we start from here and essentially stop before we get to the next data section. When we apply this smoothing procedure, the time variable gain looks a lot cleaner. So that's the essence of the methodology that we use, and the results end up looking like this. So this is the 30 gigahertz gain solution that we get for BeyondPlanck. The green line here shows our solution, and the width of this line is given by the Monte Carlo uncertainty. We also compare it with the MPipe and the original DPC solution. And we see that for 30 gigahertz, we're a bit different from the others. 30 gigahertz is the channel that is most affected by foreground uncertainties and foreground modeling in general, because that's where the foregrounds are strongest of all the 3 LFI channels. And so, and in addition, we include the WMAP polarization data in our calibration process. And this is something that has not been done by the other pipelines. So there are several, since BeyondPlanck has a very different approach when it comes to how we treat foregrounds. Essentially, we're treating everything as a joint problem, which the previous pipelines to a certain extent also have done, but we're iterating a lot more essentially and taking everything into account. And in addition, we have this extra data. So these things can help explain these differences. For 44 gigahertz, we see a lot better agreement. We see here this last part of 26, the 26 detectors is the region that Håvard talked about that we just cut out because of the poor performance there. But for 44 gigahertz, we're pretty spot on with both earlier pipelines. The same goes for 70 gigahertz. We're quite close to the M-pipe solution, whereas DPC is systematically higher in general. So these are the solutions for the gain, and the gain also has, or the calibration in general has effects on other products, since this is a global thing, and the gain affects essentially all parts of the experiment. So we can look at a couple of other products to see how whether these differences in gain solutions affect any of the other derived products. So first of all, we have this correlated noise stripes that Håvard mentioned. We see here that the final solution that we get have these heavy correlated stripes in the polarization maps for correlated noise. And a lot of effort has gone into trying to figure out what these are, and we've tried several things like removing PIDs, and lately now we've tried reducing the smoothing windows or the size of the smoothing windows to see if that did anything, and that did in fact help the correlated noise stripes, but it also made the gain solution a lot more or a lot worse behaved. So far we have not reached a good conclusion on how these stripes appear, and that's a topic for future research as well. And then we can look at the difference maps between the pipelines. So here we have 30 gigahertz, 44, and 70. And we have the BeyondPlanck minus DPC and BeyondPlanck minus N-pipe differences. If we start by looking at the N-pipe differences here, we see that all of them have this dipole structure, which is aligned with the solar dipole. So that means that essentially we have a calibration difference. That's what these maps are telling us. An interesting thing to note is that the dipole switches signs here, so the different switches signs, which means that, I mean, the relative calibration between these bands between the two pipelines change. Next up is the DPC difference maps, and we see here again a characteristic structure which is more quadrupole-like, and this is possibly due to bandpass mismatch in the DPC data, which could give rise to stuff like this. For polarization, the most interesting thing is the 30 gigahertz, where the foregrounds are, as I said, stronger and affect uncertainties more, or affect the calibration more, I mean. And we see, especially for the DPC difference, we have this quite characteristic structure. And this structure looks a lot like this template that was released by DPC, which describes the gain uncertainties in their maps because of foreground errors or foreground modeling errors. So this is basically an iterative template that or a template that comes from iterating over several iterations of gain and foreground fitting. And so they describe the gain uncertainties. And when we overplot our differences between DPC and these templates, we see that they are exhibiting some of the same structures. So that tells us that maybe these or probably these structures come from residual stuff in the DPC maps. Then we also do another comparison where we compare the 30 gigahertz maps from each pipeline with a WMAP K map. So we scale the WMAP K map up to 30 gigahertz by assuming a certain spectral index of -3.1. And then we take the difference between our 30 gigahertz map, the MPipe 30 gigahertz map, and the DPC gigahertz map, and then WMAP K-band. We see that BeyondPlanck residuals are in general lower here than for the two other pipelines. And we also see that what remains of the residual here seems to share or have this structure given by another template that was released by WMAP, which describes the basically the template trying to characterize the modes of the experiments that are poorly measured. And this, since this is what this template describes, it means that if we are able to combine WMAP data or time domain WMAP data with time domain Planck data, these are modes that should be essentially lifted or go away. So we have a hope that when we're able to extend the BeyondPlanck framework to WMAP data, these residuals should be decreased even further. Furthermore, it's not such a big surprise that we have lower residuals, given that we're using WMAP polarization data for our calibration, whereas the two others don't. So we're using Ka band polarization data to calibrate. Right, so those are the results. These are the conclusions that I've written down. We have a working calibration solution where we sample everything jointly, or sample again jointly with the noise and sky signal and everything else. There are certain differences from previous pipelines, especially for 30 gigahertz, which is the most dominated by foreground uncertainties and errors. We have some residual problems with the correlated noise stripes that we want to investigate further. And we have an overall better fit to WMAP polarization data, and that which should become even better when we include WMAP time domain data. Thank you to the funders, and if there are any questions, I can take those now.
Thank you, Eirik.